Hello, and welcome to Physics Lab. We're going over projectile motion. I have the same thing that I wrote. So the purpose of this is to describe projectile motion of two dimensions and compare three models for projectile motion. The first one is an observed model that we took a video of. The second is assuming there's no drag and coding the simulation. And the third one is assuming that there is drag. So the most important principles for this is the position update formula, velocity update formula, drag force equation, gravity force equation. We'll be using V final because we can assume that it is a non-constant force when we start working with drag. So the main result is that the drag model varied more than expected from the actual model, and that drag is rather insignificant in the totality of this. And drag, when it was calculated just between two time periods, it varied a lot between just about every single time period, and then the most accurate one way overestimated the amount that it would change the projectile in its course. So here we use V average for the entire model, and getting a trend line, of course, from the measured, and using position and velocity update formulas with drag for the x direction. So main physics ideas is that drag is greatest at its high velocities. This is a rather low velocity, so the drag is not going to be very strong. It is also a spherical object, and this will have much less drag than, say, well, the paper crumpled is we can assume is spherical, which will have much less drag than just a flat sheet of paper. Then we're using velocity and position update formulas to predict projectile motion. Assumptions, as we were saying, that the paper wad is perfectly spherical, and we're assuming that this is just a perfect ball. If it turns or spins in the air, that would affect it, and there would also be changes in the drag if it's not spherical, but we're assuming that it is spherical. In the first model, drag is insignificant, and velocity does not change the x direction. The second model, drag is significant, the drag coefficient does not change. If in theory, the ball is not spherical and it moves and it rotates while it's in the air, this would change the drag coefficient to not be constant the entire time. So the system is the ball, of course. The surrounding is the air, the earth, the table. The earth, the next, gravity force, the air creates drag. And here are our initial conditions that we measured from the video and using tracker. So encoding, this is our setup. Again, initial conditions on the left, and that B was taken from two different time periods, and then just solving for B in this drag equation. On the right, we go through it, we calculate FG, F drag, F net, and then use position and velocity update formulas, change delta T, and then we plot it. So in the no drag model, this is what it looks like. This is on the left, we can see the trajectory of the object. It's position versus time, and that is linear in the x direction. Velocity versus time is constant in the x direction. Position versus time is nonlinear, but velocity versus time in the y direction is linear. That is a constant change due to gravity. The drag model, sorry, that image is covering up the text. It looks significantly different. Velocity is not constant or linear in either direction, and there is a curve and a nonlinear trajectory in the x direction this time. So we're doing experiment analysis. Here's the video. Similarities and differences. This green line is going to be including drag. The orange is the first simulated with no drag, and blue is going to be the actual what was measured in tracker. We can tell that when accounting for drag, it severely influences the rest of the equation and the outcomes of this. But we can tell that the predictions without drag are significantly closer to the actual output than when accounting for drag in this case. We just don't have a precise enough measurement using tracker and a wad of paper as our point mass to accurately describe the force of drag. So some sources of error, as I just said, drag constant is not constant, ironically, and tracking the object is not precise enough. Each time frame will give you a different drag constant when you calculate it. So I just took one that looked the best of it, and this is the best that I got out of it. So what does it mean? By looking, extending the calculation and trying to find terminal velocity. On the left is no drag, and there is no terminal velocity when there is no drag. When we include velocity, and just in the time frame from 0 to 0.4 seconds, we can tell that the y is slowing down and is changing, and is reaching some kind of limit. And when I extended it out to 5 seconds, that limit became negative 2.85 meters per second, and that would be the terminal velocity. So what if we drop it from a standstill position, since our y was 0, and the what if is theoretically we toss it up, we're going to assume that we're just dropping it from a standstill position with zero y velocity, and it will reach the ground at the same time because gravity only affects it in the y direction. And x and y velocities of components are completely independent from each other in this case, so whether it's moving in the x direction or not does not dictate whether it will hit the ground at the same time. And it will hit the ground at the same time. Thank you very much. I hope you enjoyed. I hope you have a great day.